In the following examples we determine the electric field around different source charges by applying Coulomb's law. We start with the simplest example, where we compute the electric field created by a point charge q in a given point P, which is in the vicinity of the source charge. For a given reference point O, the position vector of the point charge is denoted by r0 and the position vector P determines the point P. The vector r is the difference of the position vectors, and its length is equal to the distance between the point charge and the point P. If we place a test charge qp at the point P, then we can use Coulomb's law to describe the electrostatic force exerted on the test charge by the source charge. Here the charges are like charges and the point charge q repels the test charge. We know that the electric field strength E in the point P is given by the force F acting on the test charge divided by qp, the amount of test charge. Coulomb's law tells us that the force F is given by 1/4 pi times epsilon naught, times the ratio of q times qp to the square of the distance r between the charges, times the unit vector pointing from the source charge to the test charge. Since we see qp in both the numerator and the denominator of the fraction in the right-hand side, we can drop qp. As a result, we obtain the electric field E in the point determined by the vector r, which is equal to 1/4 pi epsilon naught, times the ratio of the charge q to the square of the length of r, times the vector r divided by its length. This formula shows what we expected. The distribution of the electric field is spherically symmetric around the charge q, and the electric field strength E points radially outward from the source charge. The magnitude of the vector E is inversely proportional to the square of the distance from the charge. We can also express this formula in the terms of the position vectors of the charge q and the point P. Now we can determine the electric field strength everywhere around the charge q. For example, if the source charge is equal to 1 Coulomb, then the field strength in the distance of 1 meter from the charge is equal to 9 times 10 to 9 Newton per Coulomb. This result simply follows from the fact that the multiplicative factor 1/4 pi times epsilon naught is equal to 9 times 10 to 9 Newton meter squared per Coulomb squared. We have seen that the electric field strength around the point charge q is inversely proportional to the square of the distance from the charge. Then we can specify the number of the field lines originating from the charge plus q or terminating at the charge minus q. This is equivalent to the specification of the density of the field lines, which can be defined as the number of the field lines passing through an area perpendicular to the field lines divided by the area. Now we accept the following convention. We draw the field lines in each point of the space such that the density of the electric field lines in a point gives the magnitude of the electric field strength E in that point. That is, the number of the field lines passing through a unit area perpendicular to the field lines gives the magnitude of the electric field strength E at the unit area. This relationship between the density of the field lines and the electric field strength is obviously a local definition. For inhomogeneous electric fields, the infinitesimal unit area element provides the local value of the field strength. If the spatial distribution of the electric field exhibits some symmetry, then we can also use a surface over which the magnitude of the field strength is constant. We count the field lines passing through the surface, and divide the result by the area of the surface. The spherically symmetric electric field around the point charge q is a good example for the latter case, where the magnitude of the electric field strength follows the inverse square law, and it is constant over any sphere with a point charge in its center. Let us enclose the charge q with such a sphere with an arbitrary radius r, where the surface area as of the sphere is given by 4 pi times r squared. All the electric field lines originating from a positive charge or terminating at a -1 will cross the sphere. Then we obtain the number of the field lines passing through the sphere, if we multiply the density of the field lines on the spherical surface by the area of the sphere. It follows from our convention that the density of the field lines is simply the magnitude E of the electric field strength, whereas the area of the sphere is given by as. For the point charge q, this gives q divided by 4 pi times epsilon naught times r squared, times the area 4 pi r squared. We can reduce this expression to q divided by epsilon naught. Then we state the following. The number of the field lines originating from a positive charge q, or terminating at a negative charge q, is equal to the amount of charge q divided by the vacuum permittivity epsilon naught. We have already explained that the principle of superposition can be applied for a set of electric fields produced by a system of point charges. Now we can see that the net electric field created by the point charges q1, q2, Qn and an arbitrary point P is given by 1/4 pi times epsilon naught, times the sum of the ratio of qi to ri squared, times the vector ri divided by the length of ri, for the index I from 1 to n. Here the vectors are I point from the point charge qi to the point p. In the sum, each point charge appears with a weighting factor, which is proportional to its amount of charge and inversely proportional to the square of its distance from the point p. In the next example we will study the electric field around an electric dipole. An electric dipole is defined as a couple of equal but opposite point charges plus q and minus q separated by a distance d. By default, the direction of electric dipoles determined by the vector d is always from the negative charge to the positive one. The midpoint between the positive and negative charges is called the center of the dipole. We introduce the electric dipole moment p of a dipole as the product of the charge q and the vector d. The SI unit of the dipole moment is Coulomb meter. This quantity is not unique in the sense that the dipole moment does not change if we modify the charge q and the distance d such that their product remains the same. However, we will see that the dipole moment arises in a natural way in the description of the electric field around a dipole. We have already seen the electric field lines of two opposite charges places near each other, where the field lines are directed from the positive charge to the negative one. The figure shows that the topology of the electric field, that is the structure or the distribution of its field line around a dipole, exhibits a rotational symmetry around the axis of the dipole, and a reflection symmetry about its equatorial or transversal plane. If we change the charges plus q and minus q by the same amount, we do not break the symmetry of the field geometry. We change the magnitude of the electric field strength around the dipole, but its direction remains the same everywhere. As a result, the geometry of the field lines remains the same, that is, the field lines still have the same distribution. By changing the magnitude of the electric field, we modify the density of the field lines, whereas their geometry describing the direction of the electric field does not change at all. The figure shows that the density of the electric field lines around a dipole with the charges 2 times plus q and minus q is greater than the one for the dipole with the charges plus q and minus q. Then the number of the field lines passing through a unit area perpendicular to the field lines gives a greater magnitude of the electric field everywhere around the dipole. Since the electric dipole is a simple system of point charges, we can apply the principle of superposition for electric fields. This tells us that the electric field strength of a dipole is the vector sum of the electric fields of the positive and the negative charges of the dipole. First, we study the electric field of a dipole at special locations, such as on the axis and the equatorial plane of the dipole. Then we will determine the electric field in an arbitrary point in the vicinity of the dipole. In the first case, we determine the electric field of the dipole along its axis, that is, in a point P on its axis at the distance r from the center. In the point P, the electric fields E sub plus and E sub minus created by the charges plus q and minus q are parallel with the axis, but E sub plus points outward and E sub minus points inward. The distances of the point P from the charges plus q and minus q are given r minus d over 2 and r plus d over 2, respectively. Then the magnitude of the electric field E sub plus in the point P is equal to 1 over 4 pi times epsilon naught, times the charge q divided by the square of r minus d over 2, whereas the magnitude of the electric field E sub minus is equal to 1 over 4 pi times epsilon naught, times the charge q divided by the square of r plus d over 2. Since the point P is closer to the positive point charge than to the negative one, the electric field E sub plus is stronger in that point than the electric field E sub minus. By applying the principle of superposition of electric fields, the net electric field can be written as the vector sum of the electric fields. Since these fields are parallel with each other but have opposite directions in the point P, the net electric field E points in the direction of the field E sub plus. Then the magnitude of the vector field E of the dipole is given by the difference of the magnitudes of E sub plus and E sub minus, and we obtain q divided by 4 pi time epsilon naught, times 1 divided by the square of r minus d over 2, minus 1 divided by the square of r plus d over 2. We can rename the fractions in the bracket with a common denominator, and subtract them, which gives the square of r plus d over 2 minus the square of r minus d over 2, divided by the square of r minus d over 2 times the square of r plus d over 2. After simplifying this expression, we obtain 2 times r time d divided by the square of r squared minus d squared over 4. If the spatial extension of the dipole is negligible with respect to the distance of the point P from the center, that is d is much smaller than r, we can approximate this result as the ratio of 2 times d to the cube of r. Then the magnitude of the electric field of the dipole is equal to q divided by 4 pi times epsilon naught, times the ratio of 2 times d to r cubed. Since the dipole moment P is defined by the charge q times the vector d, the electric field E of the dipole in an arbitrary point along the axis is given by 1 over 4 pi times epsilon naught, times 2 times the dipole moment p divided by the cube of the distance r of the point from the center. We see that the electric field points in the direction of the vector d along the axis. This is also the case for the point p placed in the left-hand side of the dipole. Since the electric field E sub minus is stronger there than the electric field E sub plus and it points inward the center, the vector sum of the two electric fields still points in the direction of the vector d. In the second special case we study the electric field of a dipole with the charges plus q and minus q separated with the distance d in the equatorial plane of the dipole, which is perpendicular to its axis and crosses it at the center. Any point P on the equatorial plane at a distance r from the center has the same distance from the positive and the negative charges, which is equal to the square root of r squared plus the square of d over 2. Then the magnitudes of the electric fields E sub plus and E sub minus are also the same in that point, which are equal to 1 over 4 pi times epsilon naught, times q divided by r squared plus the square of d over 2. We can apply the superposition principle again and use the parallelogram law to construct the electric field strength E of the dipole in the point P. By virtue of the symmetry of the parallelogram spanned by the vectors E sub plus and E sub minus, the orthogonal projections of the vectors on the equatorial plane cancel each other out. At the same time, their orthogonal projections on the axis can be summed up, which are equal to the magnitude of E sub plus times cosine theta and the magnitude of E sub minus times cosine theta. Since the magnitudes of E sub plus and E sub minus are the same in the point P, the electric field E is equal to 2 times E sub plus times cosine theta. Here cosine theta can be expressed by the ratio of d over 2 to the square root of r squared times the square of d over 2. Now we can write that the magnitude of the vector E is equal to 2 over 4 pi times epsilon naught, times q over r squared plus the square of d over 2, times d over 2 to the square root of r squared times the square of d over 2. Then we obtain q over 4 pi times epsilon, times d over 2 divided by the r squared plus the square of d over 2 to the power of 3 over 2. If we assume that the distance r of the point P from the center of the dipole is much greater than the distance d, we can approximate the fraction with the ratio of d to r cubed. Then the electric field can be written as q over 4 pi times epsilon naught, times d over r cubed. Since the dipole moment P is equal to q times d, the electric field E of the dipole in any point on the equatorial plane of the dipole is equal to minus 1 over 4 pi times epsilon naught, times the dipole moment P divided the cube of the distance r of the point from the center. The minus sign in the right-hand side of the formula indicates that the electric field in the equatorial plane and the dipole moment have opposite directions, as seen in the figure. After having determined the electric field of a dipole in special cases, let us study the general case, and calculate the electric field of a dipole with the point charges plus q and minus q in an arbitrary point P. We assume that the distance d of the charges from each other is much smaller than their distances from the point P, which are equal to the lengths of the vectors r sub plus and r sub minus, pointing from the charges to the point P. That is, the length of the vector d is much smaller than the lengths of the vectors r sub plus and r sub minus. If we apply the principle of superposition for the electric fields E sub plus and E sub minus created by the point charges plus q and minus q, we can write that the electric field E around the dipole is equal to the vector sum of E sub plus and E sub minus. Now we substitute the result obtained for a single point charge into this equation, which gives 1 over 4 pi times epsilon naught, times the ratio of the charge q to the square of the length of the vector r sub plus, times the vector r sub plus divided by its length, minus 4 pi times epsilon naught, times the ratio of the charge q to the square of the length of the vector r sub minus, times the vector r sub minus divided by the square of its length. Then we have q over 4 pi times epsilon naught, times the vector r sub plus divided by r sub plus cubed, minus the vector r sub minus divided by r sub minus cubed. Our aim is to express the distances in this formula in the terms of the distance r of the point P from the center of the dipole. If the vector r points for the center to the point P, then the vector r sub plus can be written as the vector r minus 1 over 2 times the vector d. Similarly, the vector r sub minus will be the vector sum of the vector r and 1 over times the vector d. If the angle between the vector d and the vector r is denoted by theta, we can apply the cosine theorem to express the squares of r sub plus and r sub minus as the square of r, plus the square of d divided by 2, minus or plus 2 times d divided by 2 times r times cosine theta. We can factor r squared out and we obtain r squared times 1 plus the ratio of d squared over 4 minus or plus d times r times cosine theta to r squared. Now we can write that our sub plus or minus to minus 3 is equal to r to minus 3, times a factor to minus 3 over 2, where the factor is given by 1 plus the ratio of d squared over 4 minus or plus the scalar product of the vectors d and r to r squared. The right-hand side can be written as r to minus 3, times 1 plus x to minus 3 over 2, where x is defined by the ratio of d squared over 4 minus or plus the scalar product of the vectors d and r to r squared. We have assumed that the size of the dipole is negligible with respect to the distance between the dipole and the point P, and the length of the vector d is negligible to the length of the vector r. Therefore x is small, and we can use the Taylor expansion of the function 1 plus x to n, which is 1 plus n times x, plus n times n minus 1 over 2 times x squared and so on to approximate the result. Then our sub plus or minus to minus 3 has the first order approximation of r to minus 3, times 1 minus 3 over 2, times the ratio of d squared over 4 minus plus the scalar product of d and r to r squared. Now we can write the electric field E of the dipole as q divided by 4 pi times epsilon naught, times the vector r sub minus the vector d divided by 2 over r sub plus cubed, minus the vector r sub plus the vector d divided by 2 over r sub minus cubed. If we reorder the terms, we obtain q times the vector r over 4 pi times epsilon naught, times r sub plus to minus 3 minus r sub minus to minus 3, minus q times the vector d times divided by 2 over 4 pi times epsilon naught, times r sub plus to minus 3 plus r sub minus to minus 3. The approximation of the first term in the right-hand side gives q times the vector r over 4 pi times epsilon naught, times the ratio of 3 times the dot product of the vectors d and r to r to 5. The approximation of the second term can be written as minus q times the vector d divided by 2 over 4 pi times epsilon naught, times 2 over r cubed, times 1 minus 3 over 2 times d squared divided by 4 over r squared. Let us inspect the second term. We see that the second term in the parentheses is proportional to d squared over r squared, which is negligible with respect to 1. Therefore we will keep only the first term in the parentheses and drop the second one. As a result, the approximation of the electric field created by a dipole is given by 1 over 4 pi times epsilon naught, times the ratio of 3 times the scalar product of the vectors p and r to 5, minus 1 over 4 pi times epsilon naught, times the vector p divided by r cube. Therefore, the electric field E created by a dipole with the dipole moment p in the position r is given by 1 over 4 pi times epsilon naught, times 3 times the scalar product of the dipole moment p and the position vector r times the vector r over r to 5, minus the dipole moment p over r cube. Since this formula is linear in the dipole moment p, which is proportional to the charge q, the electric field strength of the dipole is directly proportional to its charge. The formula also shows that the direction of the electric field remains the same in any given point if we change the charge of the dipole. That is, the density of the field lines depends on charge, and not their topology. We also regain the special cases from this formula. If the position vector points from the center to another point on the axis A of the dipole, then the dipole moment p is parallel with the position vector r. This fact allows us to write the dot product of the vectors p and r times the vector r as the dot product of the vector r with itself times the vector p. As a result, the first term in the square brackets is equal to 3 times the second one, which gives 1 over 4 pi epsilon naught, times 2 times the dipole moment p divided by the cube of the distance r from the center of the dipole. This is the formula which we derived for the electric field along the axis of a dipole with the dipole moment p. If the position vector points from the center to a point on the equatorial or transverse plane t of the dipole moment p is perpendicular to the position vector r. Then the dot product in the first terms in the square brackets vanishes and we have only the second term. That is, the electric field of the dipole is given by minus 1 over 4 pi epsilon naught, times the dipole moment p divided by the cube of the distance r from the center of the dipole, which is the expression we have obtained for the electric field in the equatorial plane of the dipole. From the general formula describing the electric field of the dipole we can determine the components of the electric field strength in a given point P, if we attach a Cartesian coordinate system to the dipole such that its origin is located at the center of the dipole and its x-axis points in the direction of the vector d. In this coordinate system, the components of the position vector pointing to the point P is given by the coordinates x and y, and the x component of the electric dipole moment is equal to P, which is q times d, while its y component vanishes. These vectors will be used to calculate the components Ex and Ey of the electric field strength of the dipole. The x component of the electric field strength can be written as 1 over 4 pi epsilon naught, times 3 times the dot product of the vectors p and r times x divided by r to 5, minus p divided by r cube. We can write the dot product of the vectors p and r as the product of their lengths times the cosine of the angle measured between them, and we can factor out p over r cubed from the terms in the square brackets. Then we have 1 over 4 pi times epsilon naught, times p over r cubed, times 3 times x times cosine theta divided by r, minus 1. Since x divided by r is equal to cosine theta, we obtain 1 over 4 pi times epsilon naught, times p over r cubed, times 3 times the square of cosine theta, minus 1. The y component of the electric field strength is given by 1 over 4 pi times epsilon naught, times 3 times the dot product of the vectors p and r times y divided by r to 5. This expression can be written as 1 over 4 pi times epsilon naught, times 3p times y times cosine theta divided by r to 4. Since y divided by r is equal to sine theta, we obtain 1 over 4 pi times epsilon naught, times 3p times over r cubed, times sine theta times cosine theta. The angular dependence of the components of the electric field strength clearly shows that the electric field is parallel with the axis of the dipole on the axis. Here theta is equal to 0 and cosine theta is equal to 1. As a result, the x component of the vector E is equal to the magnitude of the expression describing the field on the axis, while its y component vanishes since sine theta is equal to 0. In the equatorial plane of the dipole theta is equal to 90 degrees and cosine theta vanishes. Then the x component of E becomes negative, and its magnitude is given by the expression derived in the equatorial plane, while its y component still vanishes. That is, the electric field strength is also parallel with the axis or the dipole moment p in the equatorial plane but points in the opposite direction. We could use the components of the electric field strength to determine its magnitude in an arbitrary point, but we will apply the coordinate-free expression of the vector E of the dipole in the calculation. The square of the electric field strength E is proportional to 9 times the square of the dot product of the vectors p and r, times r squared over r to 10, minus 2 times 3 times the dot product of the vectors p and r times the dot product of the vectors r and p over r to 5, plus p squared over r to 6. This expression can be written as 3 times the square of the dot product of the vectors p and r divided by r to 8, plus p squared over r to 6. Since the dot product is equal p times r times cosine theta, we have 3 times p squared times the square of cosine theta over r to 6 plus p squared over r to 6. We can factor out the ratio of p squared to r to 6, and we obtain p squared over r to 6, times 3 times the square of cosine theta plus 1. Then the magnitude of the electric field of a dipole in an arbitrary point is given by 1 over 4 pi times epsilon naught, times the square root of 3 times the square of cosine theta plus 1. The formula shows that the magnitude of the electric field strength is inversely proportional to the cube of the distance from the center of the dipole and it has an angular dependence. For a given distance from the center, the magnitude of the electric field reaches its maximum in the equatorial plane and it has a minimum value on the axis of the dipole. These formulas show that the electric field of a dipole falls faster than the one of a point charge, since 1 over r cubed is less than 1 over r squared for distances greater than 1 unit length. At small distances the electric field is dominated by whichever charges the point P is closer to, and the faster fall off of the field is the consequence of the fact that the electric fields of the charges almost cancel each other out for large distances. By applying Coulomb's law, we can also demonstrate that the electrostatic force acting between two dipoles parallel to each other is not a central force, and it is inversely proportional to the distance r between them raised to 4th power, provided the distance r is much greater than the distances between the charges in each dipole. Based on the superposition principle of electric fields, we can state that a system of point charges with zero net charge can be replaced by a dipole, where we place the sum of the positive and negative charges of the system in the two centers of positive and negative charges. For a given reference point O, the position of the point charge plus or minus qi in the system is given by the position vector r super plus sub I or r super minus sub I. Here we show the position vectors of the point charges plus q3 and minus q3. Then the centers of charges with respect to the reference point are determined by the sums of the distances of the point charges from the reference point weighted by the charges. The locations of the centers of the positive and negative charges are given by the position vectors r sub plus and r sub minus, which are equal to the sums of plus or minus q sub I, times the position vector super plus or minus sub I, divided by the sum of plus or minus q sub I for all the indices I. These vectors provide the position of the point charges of the dipole, and the sums of the positive and negative point charges in the system, denoted by plus or minus q, will be the point charges of the dipole replacing the system of point charges. If we place a body in an electric field, then Coulomb forces will act on the charge carriers and the basic constituents of the body. The electrons and the protons in atoms and molecules will be displaced with respect to each other by the electrostatic forces accelerating them in opposite directions. In insulators, this displacement separating the center of the charge for positive and negative charges is limited within the atoms and molecules. As a result, the atoms and molecules will become microscopic dipoles while the body remains electrically neutral. This process is called the polarization of matter.